So hello everyone, and welcome to today's special Polariton Chemistry webinar. My name is Stefan van den Wildenberg. I'm a postdoc at Huayu Group, UC San Diego. And today, I, along with Matthew Du and Teng Cheng, will be your host for this Polariton Chemistry Roundtable. We are enchanted to organize this roundtable, during which 4 panelists will discuss on the topic of single molecule versus many molecule strong coupling regimes. To discuss this fascinating topic, including phenomena, opportunities and challenges in each regime, it is our great pleasure to welcome Professor Prineha Narang from Harvard University, Professor Chris Giebink from Penn State University, Professor Gerrit Groenhof from Jyvaskyla University, and Professor Gilad Haran from Weizmann Institute of Science. Thank you, professors, for accepting our invite to participate in this roundtable. Before getting started with today's topic, let me walk you through the usual mechanisms of this webinar series and make a few announcements. To stimulate the exchanges amongst our community, we maintain a Facebook group called Polariton Chemistry Online Community. This group is not only intended for us to share information about the webinars, but it is also meant as a space for you, members of the vibrant Polariton Chemistry community, to share your research and ideas. So whether you're particularly excited about one of your latest publications, or if you want to share about a new position that is open in your group, please share it on the Polariton Chemistry Online Community Facebook page. If you missed one of our webinars, if you want to catch up with some details you missed in the previous session, or if you are eager to rewatch your favorite talk, please remember that we upload all of our webinars as well as our roundtables on our YouTube channel named Polariton Chemistry Webinars. If you want to keep up with webinars every month, consider hitting the subscribe button and click the bell. Finally, I would like to introduce the mechanism of this roundtable. Last week, we created a poll for you to submit and vote for what you consider being the most interesting questions in the context of single versus many molecule strong coupling. You provided us with a very interesting list of questions that are displayed on this slide, along with the total number of votes for each question. The top voted question is it possible to derive the transition from single or few molecule regime to collective strong coupling regime? While examining the remaining questions with the panelists, we realized that they can actually be related to 2 broader questions. 1, are we close to understand the basic principles that might govern the enhancement of chemical reactivity through strong coupling? And 2, can we expect single molecule particle plasmonic strong coupling to lead to useful applications in quantum optics? During this roundtable, the panelists are going to discuss on the basis of those 3 questions just mentioned. If you want to jump in the discussion, you are also allowed to ask your questions or to bring an element to the discussion. If you want to make an intervention, you can click the raise hand button, and Teng will interrupt the panelists at the appropriate time and enable your audio to ask your questions. Also, you can type your comments or ideas using the chat function so that you can share them with everyone. You can also type your questions in the Q&A, and we will try to address them during the roundtable. For the questions that are not answered due to the webinar time limit, we will collect them and send them to the panelists after the talk. So without further ado, I will now ask each of our panelists to briefly introduce themselves, after which we will move on with the discussion. So thank you for being here, and I wish you a great roundtable. So who wants to start? Gerrit or Prineha?
Because I was going to suggest to go along the order of the pictures, which means Prineha.
All right, then.
All right. Okay. And I actually have 1 slide to share, rigorously 1 slide, I promise.
Go ahead.
But I hope that this will help frame our conversation here today. Do you see it in the correct mode? Yes?
Yes.
Okay. So my name is Prineha Narang. Nobody calls me that. I go by Pri, and I've been working in the field of light matter interaction, particularly with impact on Polartonic chemistry for some time. And I have this slide here to actually show my progression in the field, but also in some ways capture the different nomenclature that exists in various parts of the community. So I started out in this field I saw the very distinguished set of attendees here, so some of you already know this story, in areas of quantum plasmonics. And there would be a lot of discussion early on in quantum plasmonics about the decay of collective excitation. So essentially a plasma itself decaying and how we can understand that first in the ultra-fast regime and then in the fast regime. So essentially what happens in the atto-femtosecond regime to then what happens in long time dynamics on the order of picoseconds, and where we can go from discussing a distribution to then maybe invoking a concept like electronic temperature, or eventually the temperature of the lattice. There, I think the language of TGFT and thinking about introducing the photon classically, even though we're talking about quantum plasmonics and we're quantizing the modes to describe the plasma itself, was sufficient. Okay. Eventually, this started to intersect with some of the work in plasmon-driven chemistry. And I want to distinguish the work happening in plasmon-driven chemistry from Polariton chemistry, because there, I think a lot of the discussion was around, there's a decay of an excitation. Now you have non-equilibrium carriers. They could be either electrons or they could be holes. They're being transported. I'm using my hands to describe things, by the way. So they're being transported to some surface, and then they're either making their way over some form of a Schottky barrier to a semiconductor, or some other resonant mechanism to a semiconductor, or into a molecular species. And there's a lot of discussion of hybridization of the molecule with the metal surface or a doped semiconductor in that context. And there's been really, really exciting work there. I want to contrast that with the work that's now happening in, thinking about QED chemistry, where we're talking about an explicit need to incorporate the quantized nature of light, so to have the photon there explicitly, as well as to have the electron and the nuclei there included in various forms. All of this, and this is all on the left of this slide here, is some of the same concepts come up in condensed matter physics, where there's been a lot of discussion of cavity control of various phase transitions. Really beautiful work by my colleague Jean Demler and others, in thinking about how you can control the order parameter using a cavity. And there, in that context, you can talk about strong coupling of the cavity to various types of polartonic excitations that you can get in materials. And that could be phonopolaritons, that could be magnopolaritons, and there's a whole zoo of these, and a lot has been written about it. And something that I hope will come out of the conversation here today is how do we not reinvent what's been done in either of those communities, and actually try and bridge that together, both from a theory standpoint and also from an experimental standpoint. Okay, with that, I will shut up and pass the baton to the next person.
Okay.
Thank you very much.
Next up, I'm Chris Giebink here at Penn State University. I don't have a slide, but just very briefly, I'm on the experimental side of things, and our work focuses broadly on organic photonics. Our involvement in strong coupling and polariton chemistry is mostly driven by an interest in understanding photo-driven reactions in the strong coupling regime. And so we've focused a lot, in particular, looking at strong coupling with charged molecules as a platform, trying to understand how things like photo-induced electron transfer get altered when you're strong coupling these transitions to a cavity mode. I think that's probably where I'll leave it, actually.
Okay, I think I was the third one on the slide. So my name is Gerrit Groenhof. I'm working in the University of Jyvaskyla in Finland, where it is deep night now. I can actually share slides to make, it always helps me to talk about my work if I have a slide. So my background, or our background, is in using so-called multi-scale molecular dynamic simulation models to study photochemistry in condensed phases. And having done that for DNA, for proteins for quite some years, we actually, with Jussi Tappari, my friend and colleague here at the university, we realized that we might also be able to use this model to bring some understanding in collectively coupled molecules in cavities. So we actually extended the model to that. And as I show you on the slide here is this QMMM model. I don't know if you see my mouse, which basically allows you to treat systems which are large, using a hybrid model between a quantum chemistry approach and something which is called molecular mechanics. So it's just a set of simple functions that allows you to treat systems with millions of atoms, and then use that method as a starting point for describing strong coupling effects in optical cavities when these molecules are in there. And the way we are looking into this is we use massive parallel computing. So we write algorithms that work parallel quite well, so you can treat large systems. And with that, we have been treating mostly electronic strong coupling, but more recently we have also moved into vibrational strong coupling. And there we try to combine these computations with experiment and try to systematically map out vibrational strong coupling effect in a limited chemical space. And yes, I'm looking forward to this discussion. I hope to learn more. And I give the word now to Gilad.
Yes, okay. Do you want to stop sharing?
Yeah, I'm looking for the stop button. Okay.
Oh, okay. So I'm actually not going to show any slide. Looks like the experimentalists don't show a slide while the theoreticians do. So we already have a phased separation here. So I'm Gilad Haran. I'm from the Weizmann Institute of Science, from the Department of Chemical and Biological Physics. My group here focuses on single molecule spectroscopic studies on a broad range of different systems. In plasmonics, over the years, we've been using single molecules to study Raman spectroscopy and how plasmonic structures may enhance it to the level that we can actually see chemical changes due to single molecules. But in recent years, we actually focused more on strong coupling between quantum emitters and plasmonic structures. In 2016, we showed that we can see vacuum Rabi splitting in a small number of quantum emitters down to the level of 1 quantum emitter. The emitters were quantum dots, semiconducting quantum dots that we inserted into plasmonic bow ties, and we could see nicely vacuum Rabi splitting using scattering spectroscopy. We then did the same experiment using electron energy loss spectroscopy inside the electron microscope, and we also used photoluminescence spectroscopy to look at these systems, and we found that there are very nice, I would say, complications that we could not understand just by looking at the experiment, and we needed some help from theoreticians, especially from my colleague and good friend Javier Espurua, and together we tried to solve what happens when you have complex photophysics in the quantum dots that couples them to the antenna, to the plasmonic antenna, and how that affects the emission or is reflected in the emission. So this is more or less what we do, and we are very interested in trying to see how we can push forward these systems of quantum emitters and plasmonic antennas. How can we increase or enhance the coupling between the antennas and the molecules or the emitters? How can we actually study them and understand new physics from these studies? For example, can we use them as single photon emitter systems, or can we at least walk in that direction using various tricks of quantum optics? Can we actually prove that we are at the single emitter limit using quantum optical studies, as opposed to what we did so far, which was to look at electron microscope images, and so on and so forth. And I hope that some of these issues will be actually raised during the discussion today.
Okay, thank you very much. So I think it was a great introduction, actually, because it sets the stage for the whole discussion. And now, if you allow me, I will continue sharing or share again that slide with the questions we were to discuss today. So maybe we could start like with the first questions and try to summarize how close are we to actually understand those basic principles that might govern the enhancement of chemical reactivity to strong coupling. And here I want to emphasize that we do not limit this question to ground state or vibrational strong coupling, but we do include all the electronic strong coupling and the larger context.
You can also discuss things specific to single molecule strong coupling, many molecule strong coupling, or both.
Yeah. So maybe Gerrit, you have a first idea?
So it's
always
because I'm the movement, you always put it to me somehow. But
yeah,
yes,
I know, because you moved.
I can just start saying what's on my mind when I saw this question. And I think, yeah, so this is one of the key questions at the moment. And I think that probably 100% of the participants here are after that. I think, well, I dare to say that for electronic strong coupling, I think we have a good understanding of what could be the effect of strong light matter coupling on the chemistry. And I think this idea has been pushed. I think one of the first papers was by Johannes Feist, where they show that the polaritonic energy surfaces are different from the original potential energy surfaces on which normal photochemical reaction would happen, and that could lead to effects such as delays. And there has been other simulation work again, where coupling closer to, let's say, a conic intersection was shown to give effects because it locally changes the potential energy surfaces. It opens up a decay channel that could lead to additional decay, and this way influence where the molecules go back to the ground state. And I think I also dare to say, but I invite everybody to disagree with me, that I think to model to model electronic strong coupling, and we can use the standard methods of quantum chemistry much easier than for vibrational strong coupling. Like we have seen that we can model quite accurately photochemistry if the chromophores are not too complex and not too big, even in protein systems, and experimental validation of those simulations have shown that these simulations are indeed capable of capturing the essence of the photochemical reaction. And those methods are relatively easy, in my opinion, to combine if you use a simple model for the quantum optics, so like the Jyvaskyla model. So I think, yes, for electronic strong coupling, I'm quite optimistic that we will be able to understand it quite well. For vibration strong coupling, but that's maybe the next. Maybe we should stick to the electronic strong coupling first and then discuss the vibration strong coupling. So now I see that Gilad, you want to continue here.
Yeah, I actually have a question to you because you mentioned that it's rather easy to simulate excited state dynamics, but I thought that excited state dynamics are not so easy to do with full electronic structure, especially for molecules, using DFT methods and so on. So I wonder, maybe I just missed some progress in this field. I'm sure I did, because that's not my field. But I will be glad to hear more about that.
You missed one word. I said if the chromophores are not too complex or not too big.
Okay.
So, so no, excited state. So in contrast to ground state chemistry, which can be described quite well nowadays with quantum chemistry methods, in particular DFT, excited state still pose a challenge. I mean, they pose a challenge for the DFT functional. So instead, when I talk about excited state dynamics, I'm using wave function methods, multi-configurational wave function methods. And they have their weaknesses as well. I mean, you need to be very careful. These are not black box. And I hope I really said it, but I remember I said if the molecules are not too complex or not too complicated.
Yeah, you did say that. You did say that.
In that, yes. So in that
but
sense,
the question is, what does it mean, not too complex? I mean,
not too
number
complex.
of atoms or.
Okay, so that means that the photochemistry is happening on a well isolated state. So what we do not want is when there is a whole manifold of accessible excited states close by each other, because then we easily get small shifts in the energy of one state because of lacking some electron correlation will immediately lead to a different chemistry. So these things are very difficult to do. So I used to pick my problems quite carefully. But once you can do that, then you can combine this with the semi-classical and D methods in order to simulate what happens. And yes, this gives a qualitative picture. It's quantitative is difficult to obtain here, but that kind of picture where you see the atoms move, that you can nowadays confirm with time-resolved crystallography. So one of our first attempts here, we actually used more recently time-resolved crystallography at the free electron laser in Stanford to actually probe the changes in the atomic displacements and kind of see that this is indeed what the simulation was telling us already so many years ago. But if you give me now a system that you're interested in, I don't know if I can model that. But again, in order to understand, we're talking about the polaritonic chemistry effects. So taking a molecule for which we understand quite well the photochemistry, and we know that we have the toolbox available to describe it, like I'm thinking of reactions like excited state proton transfer, photoisomerization, where just a double bond rotation. Taking systems for which the electronic structure theory is established, and we kind of agree, all of us, that this is the proper level of theory, then that is what the systems I was talking about. So that brings me then also to the next point. In order to validate this, we need more experimental data to get the concept. And in particular, the problem is always that, for example, excited state proton transfer, I mentioned that. For that, we can do pretty well in terms of theory, in my opinion. But experimentally, that's very difficult because these things absorb in the UV. So you need to do a strong coupling in the UV. You need to be able to read out what actually happens. So this all poses problems in order to, there is no such easy, there doesn't seem to be an easy way to confirm if something is the case.
Yeah,
does that answer your concern? Chris, sorry.
I was just going to amplify the point that you were making. Right, I think at least in the case of optically driven chemical processes, we have at least several plausible mechanisms by which we can imagine that things change. But what we seem to be lacking right now, I don't think I've seen, is a direct quantitative model of an experiment that says that this is exactly the mechanism that's happening, and it quantitatively explains the changes that we observe. So far, I think it's mainly just been some experimental effects that have been seen and some plausible mechanisms to explain them, but nothing direct. I think if we can take that next step, it'll become a lot clearer. At least from, go ahead, Gilad.
Sorry, so I wanted to make a comment that I think when we are looking at these effects that we might see in electronic transitions and how they are affected by plasmonic strong coupling, then I guess there are, to me at least, there are two types of effects. One is what Gerrit mentioned, which is enhanced relaxation rates. And the other one, which is to me more interesting perhaps and more novel and exciting, is to look at really changes in the excited state potential surfaces on which chemical reactions might occur. And I actually don't even know how one might probe that on the single molecule or close to the single molecule level. I guess in condensed phases in liquids, one can do various ultra-fast spectroscopic experiments in order to probe this, but these cannot easily be adapted to the single molecule level, although people do single molecule fast experiments, like Nick Van Hulst has been doing such experiments, and other people, but that's a very, very difficult experiment to do.
Right. So since everyone's tackled a little bit of the electronic strong coupling aspect, I'll take a different tack and say something about the vibrational aspect here. I think there has been progress. I'm not going to say that the experiments there are fully understood or the experiments themselves, as was just mentioned, are fairly complex, and disentangling, no pun intended, the different effects is actually fairly challenging. But I think we and others who've been thinking about how you can meaningfully merge QED and electronic structure have been able to say things about how the cavity is acting as a mediator for these different vibrational modes, the role of inharmonicity, and how this might be impacting the chemical reactivity. Again, that's far from a quantitative agreement with a fairly complex experiment, but I think it's, we're closer. So if I could amend that question from close to are we closer? Yes, we are a few steps closer than we were when the experiments first came out. I think some of the questions that probably are hard to address, even with some of the best quantum chemistry techniques out there, when you're thinking about the correlations both in the ground state and the behavior of the entire excited state manifolds, I think it's a challenging one to treat while also incorporating the impact of the photon there. I'd further add that some of the cavities that are being considered, are possible to be considered from a theory standpoint, tend to be high Q cavities, and that's a little bit of a departure from the Q associated with the experimental effort. So I think bringing those two things closer is going to be very important. And finally, of course, wonderful things that we and others have tried to incorporate, but it's hard, thinking about the impact of salvation, thinking about some of the other aspects of the experiment that are necessary for us to again get quantitative agreement. Those are harder for us to incorporate in a theory context.
I would say a big one experimentally, at least in collective strong coupling regime, is thinking about the effects of disorder, particularly on thin films where a lot of these experiments are done. It seems like beyond some of the more exotic Polariton chemistry mechanisms like Polaron decoupling and so on, that sometimes just simple things like Polaritons averaging over disorder may be sufficient to explain some of the observations that we see. Almost, I would say overwhelmingly for us, I'm sure I'm not speaking for all experimentalists, but when we go and look for plausible or expected Polariton chemistry effects, we don't see them. We're very often disappointed. And so I would say more the rule than the exception is that you don't find anything non-trivial happening in the experiments that you do. So it's may be on our part just bad choices of systems to look at, but that is just going to have anecdotally what we tend to find.
Chris, what do you mean when you say non-trivial?
Well, I mean, something that goes beyond just, for example, the cavity field enhancements in, for example, things like photo-induced electron transfer, things that you can't just explain with simple linear optics transfer matrix modeling of the system, really.
Gerrit, did you want to jump in?
Yes, but actually not on this topic, but on something Prineha said earlier about including also the effect of the decay, of the fact that it's finite lifetime. And I think there the problem is that to do this at the theory level, simulation level, there is also the large number of dark states that determine the lifetime eventually. So that means that if you do it with a single molecule, it is still very hard to extrapolate. And I think that is one of the, that is the third question here, in fact, is related to that. Then you still need to account for these dark states. And I think the only way to do that is to do many molecules. But of course, then you have to compromise on the level of theory that you actually employ for those molecules in order to do so. Yeah, so perhaps I was a little bit optimistic when I was starting this discussion, when I said that on electronic strong coupling, I think the idea is clear. But I meant that, yeah, qualitatively, I think what can happen, I feel that we understand that. At least the two main mechanisms that also Gilad mentioned, that you have the change in the polaritonic surfaces, which have not been readily observed. I mean, there is some triplet annihilation work where this seems to be there, that there is a polaritonic state which intermediates the transition between singlet and triplet and vice versa, and which mediates the annihilation process. But in terms of reaction delays, yeah, there has not been experimental results published that show such effect. But qualitatively, sorry?
Yeah,
I think that was just a dog barking.
So, okay. Oh, you're allowed to bring dogs to work there. Okay. Yes, but the dog brought me off my thread.
Oh, no. Well, I guess one of the, just building on what was just said both by Chris and Gerrit, I think it's a subtle signature to be able to distinguish between something being modified by electromagnetic coupling that you could treat with a semi-classical model or with these transfer matrix methods versus a regime where you really need to invoke quantum optics, where you really need to invoke QED. And I think I'd be interested to see, more experiments that can either somehow dynamically go between those two regimes, or for the same system somehow say, this was a regime where we were in a semi-classical electromagnetic regime, and this is where we were in a quantum regime. Because I think there's a serious risk here of theory overkill with, invoking some of these more complex models and then realizing that the signature can be explained other ways. So, yeah, disagreeing with you, Chris. Yeah.
Excuse me, I would like to interrupt that we have several questions from the audience. So first is from Joel. Let me. It's really strange that I cannot.
Oh, you cannot? Let me. You can go ahead, Joel.
Hi, thank you guys for the very nice discussion. So I want to second Gilad's question about Gerrit's comment that there are these two different modifications that occur, one of them being an actual change in the potential energy surface and the other one just relaxation of, say, photon leakage or something like that. So, I mean, I believe that photon leakage is the most, I guess, mundane change that we all expect to occur. But the other one is just relaxation to the dark states, in which case maybe the dark states just behave like outside molecules. So then the question is it really possible to see changes in the potential energy surface, and where is the evidence? You were mentioning triplet annihilation. Can you provide some context of why people are claiming that there are changes in the potential energy surface under those circumstances?
Okay, so yes, Joel, I agree that we haven't talked about the dark states so much yet, but they do play an important role in the chemistry, because yeah, if you access the dark states, you go in there and there is so many of them, then in what we see in our work is that it is also, the party is over then, because these dark states do not really live on modified potential energy surfaces. So the triplet annihilation work is not our own. I was actually referring to a recent paper in JAX by the Burgerson group, where they show that as a function of the tuning, they can actually enhance the upconversion process. So it goes from endothermic, where it has to go up the hill, where the singlet state is actually more than just twice the triplet energy, to a situation where they go down the hill. But that was not my own work. So I just mentioned this as an example, because I think one of the problems is that there is not enough experimental data to actually validate or even know if we are quantitatively, to check if we're quantitatively correct or not. And yeah, there is this triplet annihilation works where there are effects on the photochemistry of, or at least where effects are reported in experimental work on the photochemistry. There is the spiropyran ring opening example by the Everson group many years ago, which has kind of all started this. But at the moment, yeah, we would like, I mean, if you really want to test the collective effects, what would be good to have is plasmonic nanocavities with a handful of molecules. So not 10 to the power of many, but just a handful, like 10, like has been recently achieved. The Baumberg group is achieving that. Bidot has recently published an ACS Nano where he couples like 6 or 7 molecules to a cavity. So those are the systems that now, if we put reactive reactive molecules in there, those would be the ones to study, and those would be the ones to benchmark our theory and our computations on, I think.
Okay, thank you.
Also, they have fewer dark states.
In that regard, I also want to mention the work of Andrew Moser and Jenny Clark and David Litzy and so on, where they also showed that this triplet annihilation gives enhanced photoluminescence at long times. And then we did a very simple calculation for that work, and yeah, it seemed like at very long times you really see these changes due to these new polaritonic energy surfaces. But then this is but this only works for like very slow reactions and things like that. Yeah, so okay, so I think then we kind of agree that.
What's a slow reaction in this context, Joel?
I would say it's like microseconds. So that's slow for these photochemical processes. Yes, like microseconds.
And do you think there needs to be some either energy or timescale matching between how long the excitation lives in the cavity and the timescale to reaction? So for example, would maybe a dielectric cavity be a slightly better match for than what you're asking here?
So my understanding of this is that this is all limited by how fast the decay of dark state population reaches the polaritons, because given that the polariton manifolds have very small density of states, those rates are very slow. So if you're going to really affect reactions, you need to and you're going to use this very slow process to do something, then the reaction itself needs to be slow. That will be my take on it. Yeah.
This kind of comes back to
Thank you.
Experimental distinction, where we ask whether or not we're looking at reactions changing when we excite them non-resonantly or when we resonantly excite into a polariton mode. And the two situations are very different. We have focused on resonantly exciting polariton modes because at least we know that we're absolutely creating polaritons there. In thinking about the importance of timescale, at least experimentally for us, what we've seen is that when we do see effects, it seems to be when the timescale of the reactions is not incomparable to the Polariton lifetime. So we're looking at very, very fast phenomena. When you're thinking about reactions like photoinduced electron transfer on like a nanosecond time scale, orders of magnitude longer than the lifetime of the Polaritons in most cavities, it is harder for us to, well, we don't see anything experimentally. We've had to go to systems with very, very fast electron transfer, kind of 10 to 100 femtosecond time scale, before we actually see something unusual happen in terms of what looks to us like a modification of the photoinduced electron transfer rate. The timescale seems to be critical when you're resonantly exciting the Polaritons. And then, as Joel mentioned, when you're non-resonantly exciting, you're generating a whole bunch of dark states, and then you have a relatively small number of Polariton states for these dark states to go back and interact with. Just statistically, it starts to become unlikely in order to have the Polaritons impact things when you don't start out there.
So when you resonantly excite, then you expect that the entire reaction, or is it just the first electron transfer process, completes within the lifetime of the Polariton?
In the systems that we've looked at, what the picture has essentially been is you resonantly excite into a Polariton mode, and then the vast majority of those Polariton excitations either leak out of the cavity or decohere into dark states very rapidly. But if a competing decay process like electron transfer, which will cause your Polariton to decay, if that rate is at least comparable to the decay rate of the Polariton, then you can have a small fraction of these Polaritons directly decay via electron transfer, basically undergo electron transfer. And in those situations, you end up with a different outcome, possibly more efficient electron transfer or higher rate of electron transfer in those specific cases, where you can end up seeing an experimental signature associated with that.
So I think there is one aspect that we might also add to this, which is related to something that has been discussed in the SERS literature some time ago, chemical enhancement. So people talked a lot about the possibility that inside the SERS device, you end up getting some electrons being transferred from the substrate to the molecule or vice versa. And that might lead to an enhancement of chemical reactions. And there are even examples where people saw that these were not necessarily single molecule experiments, but they were close to single molecules. They were not under a strong coupling regime, but they were under a regime where some involvement of the metallic surface was necessary in order to see the effect. And I just wonder loudly now whether removing or moving some of these reactions into a cavity where there is also a polaritonic effect might lead to even more exquisite phenomena.
I think this question is actually related to one of the questions in the Q&A from Bill Barnes, who asks, many calculations use a very high value for the vacuum cavity field, so as to allow just a few molecules to be used to reach the strong coupling regime. How realistic is this trade-off? And I think this is probably related to those plasmonic nanoparticles and those hotspots from add atoms. So yeah, just wanted to.
It's certainly a generous approximation to say that you can get to these arbitrarily high, levels of coupling, which would be near impossible in plasmonic settings, just because the plasma would actually decay in the amount of time that you need there. But it's been a necessary approximation to see some of the subtle signatures. So this is back to what Chris was saying, that without some of those parameters, at least from a theory standpoint, you start to essentially lose any of those signatures. Yeah. Which is where I'd argue that instead of trying to do this plasmonically, I saw there was another question from Arkajit that we should actually be going towards higher Q cavities where these subtle signatures are actually easier to differentiate from just an enhancement effect. Yeah.
Yes, I agree with that. And I also want to add to Bill's question that, yeah, if you want to achieve the strong coupling limit with just one molecule, for example, yeah, you have to apply very strong fields. And if you then start looking at the forces, if you just take the Hellman-Feynman forces on the atoms, what you actually see is if you go from, let's say, 1024 molecules, I always like this power of 2, 1024 molecules down to 1 molecule, you see that these forces enormously increase. And then, okay, this is where Prineha might start also commenting on. The quantum chemistry levels that the quantum chemistry theory that we use, or the computations that we do, they are usually with a finite basis set. They usually only describe one excited state correctly. So this way you avoid any electrons being stripped off, any states being accessed that can never be accessed, that would be accessed under such strong fields. So in the end, I think doing it with a few molecules actually also violates the validity of at least the model that we are using. So that's why we always try to go to a large number of molecules so that the actual effects stay small. The actual interaction with the field stays small, and you reach everything, the polytonic signatures, through the collective effects. So a single molecule pumping up the field in order to get the Rabi split and get a scene experimentally, in my opinion, and based on what we can simulate, but then again, our model is perhaps too limited, is not the same. Get very different dynamics. So the molecules are affected to a very different extent.
So you have to actually include a very large number of electronic states in the basis to account for this interaction due to the interaction with the electromagnetic field, right? And,
exactly.
and then you're running into problems because this dense manifold of electronic states actually has a lot of conical intersections, and you need really hard computations.
Mm-hmm. But that is also not, I think that is, yeah, well, that is something that I think, I cannot say, I don't have evidence, but that is, I think, not what is observed experimentally. The collective effects seem to be the ones that change the chemistry, not a single molecule suddenly feeling a very strong cavity field. And related to, this is actually also back to what Chris was saying. So I have a question. So these experiments where you see changes or where you do not see changes, do you then resonantly pump those systems like exciting the polyatomic state, or do you non-resonant pump it?
We do both, but the situations where we see changes is only when we resonantly pump into the Weizmann mode.
And do you then pump the polariton? Is it like an optical cavity where you have like a zero, the K is 0 mode, and you pump at the K0?
Yeah. So these are kind of very rudimentary, just metal cavities. So very short-lived cavity photons, and we will kind of go on resonance at a particular K, and then we'll try and excite off resonance, away from higher energy, for example, and then compare those two results. And we look for situations where we see a consistent difference that tracks with detuning, that tracks with Rabi splitting, that tracks with varying concentration of molecules in the cavity, and that's the case where there's only a very small handful of situations where you see a consistent effect emerge.
Okay, but in this case, these are time-resolved measurements. So that means there is an energy bandwidth in the laser pulse with which you excite the system. So what about if you're not at the K0? What about the wave packet just wandering off? That means different molecules being part of the polariton at different points in time. Is that also having could that also have an effect on the actually observed of the observations that you do in that case?
It's certainly possible. So the experiments that we've done most recently have been steady state, not ultra fast. But the line is so broad that I don't think we can say one way or the other. So I certainly wouldn't rule it out, I guess would be my answer.
Because that would also be a trivial explanation. Or not a trivial explanation, but that would be an effect that is kind of trivial. It might still lead to unpredicted outcomes, but
yeah. We're always trying to disentangle just simple Purcell type changes in lifetimes and so on, and make sure that those aren't causing the effects that we're seeing.
I just want to make a comment on what Pri mentioned before regarding high Q versus low Q cavities. So obviously we would like to work with very high Q cavities, But the fact of the matter is that usually these cavities have also low coupling. So if the coupling is small, you need many molecules. And if you want to go close to the level of single molecules, you need high coupling, which you cannot really obtain in these high Q cavities. So you need to resort to these really shitty and lousy plasmonic cavities that have Q factors of the order of maybe 10 or something like that. And then you win because the volume is very small, of course. And so it's a completely different regime. And the question is, I don't know, maybe somebody will be smarter than me and will figure out a way to actually bridge these two regimes. I don't know how to do that.
I mean, in the interest of time, and it's a very interesting discussion, but I think we still need to address question 2. And there are actually 2 questions from the audience that we could maybe answer before moving then. So Teng, do you see Wei's question on the Q&A?
In the chat, there is also questions.
Right, there is a question. So the question from Wei is, so what is a good number or density of molecule that theory can calculate with the number of computational power, while experimentalists can also conduct the measurements with a decent signal to noise level? No.
Gerrit, did you want to tackle that before I get my foot in my mouth?
A specific question?
Well, I can make a brief answer, but of course, if we take a relatively simple model like Jyvaskyla's model, then I would say a few thousand molecules we can model that way, not more.
Okay. And
I think if you're trying to do something explicitly with, so the methods that we've been developing in the group, the number drops at least an order of magnitude lower than what Gerrit just mentioned, especially, and this is where you start to think of more complex molecules, or if you start to involve transition metals, the situation very rapidly gets more and more complicated. So simple organics, fine, we could do a fair number, but you start to have active reaction centers, start to have nickel or cobalt in there. Life gets very bad very quickly.
Life gets bad for the people who have to do it. I mean, that's usually not me. But the thing I want to add to that is that so I hope I mentioned that it is a Jyvaskyla based model. So single excitation subspace. We don't include double excitation, triple excitation. It's just like that. And then even transition metal complexes like porphyrins and so on, they can be done. It takes a bit longer, but it can be modeled. But the question is if what you want to observe, what you want to measure, if we can actually get the observable out correctly. So for qualitative understanding, I think this is a good starting point. I mean, to think about what do I want to measure, because I did not completely understand what is, so you want to conduct a measurement, but what we have been talking about now is how do we measure, what do we want to measure? So if we have a chemical reaction, then maybe the rate is what we want to measure, but spectroscopically that is also very difficult because you have to probe the molecule inside the optical cavity in that case. But of course he cannot comment on the question, right?
We have another question. So Kishan's question, strongly coupled cavity molecule, molecular system, how much refractive index modification can we observe individually in cavity as well as in molecule after coupling, and how to measure changes in the refractive index individually?
So I think what Kishan refers to here is whether the fact that you have molecules inside the cavity actually changes the refractive index of the cavity, and that in principle can be seen by scattering. So you should be able to see some changes in the scattering spectrum. And one might argue that that one sees such effects. So phonoresonances, for example, these are effects that are due to the coupling between the molecular system and the cavity, which is not a strong coupling, but just an interference effect. And that really changes the optical properties of the cavity in a way that you get suddenly deep in the scattering spectrum. And I think that's one way to see such changes. If there are more global changes in the refractive index of the cavity, I would say that would be, I'm not quite sure how to measure them.
Maybe I'm not sure I fully understand the question, but something related that we've been looking at lately has been electroabsorption in strong coupling regime, where you apply an electric field between your two mirrors and you induce a shift in the complex refractive index of the molecules within the cavity. And the question that has been interesting for us is seeing whether a simple linear optics transfer matrix can reproduce that. Because in principle, if I just think about it from a classical standpoint, I've got my molecules in a cavity, I apply an electric field, I shift their refractive index, and then I see some result, which I can model with transfer matrix. And that's experimentally distinct from having the electric field actually shift the polariton resonances. And so there are two different results, kind of taking this kind of linear classical approach to thinking about it versus just directly acting on the polariton states. And experimentally, what we see is that you're acting directly on the polariton states. You can't just view it as electric field acting on the medium inside the cavity and then the cavity just basically acting as a filter, that you see the outcome of that, which for us was kind of interesting. Maybe obvious to the theory folks, but I mean, that's an example where you kind of get what I would consider a non-trivial effect of changes in refractive index within the cavity.
Thank you all for your questions and answer. So we only have a few minutes left, so I propose that we spend them to try and give a few or some perspective on question 2. So according to you, can we expect single molecule particle plasmonic strong coupling to lead to useful applications in quantum optics? So maybe Prineha, do you want to start on this?
You know, I'm typically an optimist, but on this one, I'd have to say, I think, you know, if we're thinking of applications, for example, controlling the behavior of emitters, or, you know, thinking about applications in this context of some quantum technology, I'm a little bit pessimistic that plasmonics will be the way to go. I'd have a slight preference for something using dielectric or other genres of coupling to these molecules. Having said that, I'm happy to be proven wrong on this. I'd be, you know, delighted to buy whoever proves me wrong a very nice beverage if they get this to work. So.
Gilad, having a special interest in single molecule plasmonic interaction, maybe you have a particular perspective.
So I totally agree. I totally agree with Pri that at least in the coming future, I don't foresee that we can compete with quantum optics applications in high Q cavities at low temperatures and so on. But we can try maybe to find some niche experiments that would lead to very interesting results that would be useful also to do at room temperature with broad lines, fast relaxation times, and so on. For example, energy transfer experiments where you look for energy transfer between perhaps different emitters in the same cavity, and to try to see whether that's even possible, to see whether you can see interesting effects of perhaps emission of more than one photon at the same time from such cavities because of the joint coupling between emitters, and such effects that could be interesting. I don't know what exactly to look for yet, but this is something that we've been thinking about, and perhaps this is something that is feasible to do. The future we'll see, I don't know.
Do any of the other panelists have comments about this question?
Yeah, I had a bit more pragmatic and maybe a bit more narrow view on that. I thought this is what we need to validate the theoretical methods, the computational methods. Like that's also a useful application in my eyes.
Oh yeah, that's true. Yes.
But yeah, I think the question is meaning more like something application, like maybe you make an optical switch or an optical transistor, I guess, but I have no idea.
the main issue being like the small lifetime of these plasmonic resonances. Do you have some thoughts about using surface lattice resonances that have a much longer lifetime and may preserve the enhanced field in proximity of those particles, but combining with a very large lifetime? Maybe that would lead to some quantum optics applications.
But in that case, for these lattices, the lifetime or the line width depends on where you are in the lattice. So these diffractive modes, they have a long lifetime, and closer to the plasmonic particles where you want to have the field enhancement, the lifetime is again that of the particle. So I'm not sure if that is giving you like, yeah, you have a K factor dependent decay, so to speak. And if you're close to the plasmonic particles, there you have a low Q factor again.
Okay.
But I don't know. I mean, it is too far out of my own comfort zone.
Okay, so in the interest of time, I'm gonna have to conclude. But before, I want to ask all of you if you have any final remarks on this conversation, on this roundtable.
Looks like a lot of work for the future.
Yeah.
Still a lot to learn.
I certainly think for the new spectroscopies and people coming in from various other communities that are bringing spectroscopic techniques, it's been really enlightening, and I'd love to at least personally collaborate with some of the folks. So I see friends and colleagues here in the attendee list, and I think there's a lot more to come from this field.
Yeah, and so I second that, and I think what makes this Polariton chemistry and these questions, particular question ones, are interesting. I mean, I don't know how often this has happened in the last decades that a chemistry result kept physicists puzzled for so many years. I mean, maybe there have been many examples, I do not know, but this is just something that, yeah, these effects have now been reported for many years, and we still don't really know why it is. We cannot really predict what we have to build in order to use this to control chemistry in a systematic way. I mean, we don't even know if it's systematic or if it is actually, if it's general, if it's just very molecule specific, if there is some aspect of a molecule that gives, for whatever reason, an effect. So I think it is very exciting in that sense, that everything is open, in my opinion.
Thank you very much. We may have a last chat from the conversation. It's just a remark on the SLR. So maybe we will tackle this offline. So, okay, thank you very much all for this fascinating roundtable. It was really great, and it gives us a nice perspective on the future of this field. And thank you everyone for your participation into this roundtable. I mean, the audience, as well as the panelists, of course. And so before closing today's session, please allow me to introduce next month Polariton Chemistry webinar. So we will have the pleasure to welcome Professor Tal Schwartz from Tel Aviv University. The webinar will take place on December 8th at the usual time, 9 a.m. PST. The registration can be made both through this link as usual and in the reminder email that will come to you 1 week before the event. In the meantime, I wish all of you a great month. See you next time.